Welcome to this FP2 video on nth roots of a complex number. So we can use De Moivre's theorem to solve an equation of the form z to the power n equals w, and z and w are complex numbers. Okay, so just kind of messed that up, but z, w are elements of the complex numbers. And this is equivalent of finding the nth roots of w. There's a couple of conditions to this. So z and w are non-zero complex numbers. And then when n is positive integer, then this equation, z to the power n equals w, has n distinct solutions. So to find the solutions, we're going to use De Moivre's theorem, and we need to take into consideration that the argument of a complex number is not unique. So for now, we've done that z, or any complex number, can be written like this, plus I sine theta. Okay, but we can also write it like this. So this now will be a little bit new to you, but you should understand. So for cos, instead of cos theta, is cos theta plus 2k pi, because multiples of 2 pi will give me the same values. And I sine theta plus 2k pi, where k then is any integer. So k can be positive or negative. Obviously when k equals 0, we get this. And then k equals 1, that's then just, a full rotation on, isn't it? So it gives me the same value, the same answer, but of course it's a slightly different solution. Okay, or slightly different complex number, but equivalent. So that's what we're going to use to be able to solve equations of this form. So let's start with a nice straightforward one. So here it is, we're going to solve the equation z to the power 4 equals 1. Now this is probably the simplest example that we can basically get. So I've got that z to the power 4 equals 1. So z to the power 4 equals 1. Now writing this in terms of its modulus argument form, that would be cos 0 plus I sine 0. Because cos of 0 is 1 and sine of 0 is 0. So we eliminate the I, the imaginary part, which we don't have an I in here. So that is this written in the modulus argument form. So z can be written as r cos theta plus I sine theta. And then this is obviously raised to the power 4, because that's z to the power 4. And then this side, I'm going to write this, but I'm going to write it in its general form, and its general form will be 0 plus 2k pi plus I sine 0 plus 2k pi. Okay, that's just because if I add multiple 2 pi's onto here, I'll get the same value, and the same with this one. Okay, so that's all I'm doing, is rewriting this as its general form there. Now, for the left-hand side, I'm going to apply De Moivre's theorem. So this is going to become r to the power 4 cos 4 theta plus I sine 4 theta. And then the right's just staying the same at the moment. And of course k is an element of the integers. Okay, so I'll just pop that there, but you don't need to worry about that. So what we've got here is r to the power 4 equals 1, because this now is this, isn't it? So that's basically going to give me that r equals 1. And 4 theta is equal to 0 plus 2k pi. And I don't have to worry about the 0, so I'll just call it that. So 4 theta equals 2k pi. So what we've done here is compare our values of r and then compare our angles. Okay, so that's what gives me the r and what gives me the angles. And then the next step is to substitute in consecutive values of k. Okay, we need to use consecutive values so that we can find the distinct roots. So we'll start off with k equals 0. This we've technically already kind of found. You'll recognize this one. So when k equals 0, then theta equals 0, isn't it? Okay, because when k is 0, this right hand side is 0, so then theta must be 0, because 4 times 0 is 0. So z1 is equal to cos 0 plus I sine 0, which we know is 1. So that's the first one done. Now, next one, now look at k equals 1. Okay, now when k is 1, this is going to be 2 pi. So 2 pi divided by 4. So theta is going to be 1/2 pi. So pi by 2. So that means my second solution, Z2, is going to be cos pi by 2 plus I sine pi by 2. And cos of pi by 2 is 0 and sine of pi by 2 is 1. So this one is just going to be equal to I. Now from here on out there's kind of two approaches to take. So ultimately we are trying to make sure that the argument is always in the interval of minus pi to pi. And if we end up with a value outside of that interval, we can add or subtract 2 pi to it. So I can continue on doing k equals 2, k equals 3. Okay, or I can also switch to negative ones. So if I switch now to k equals -1, and I'll show you what I can do alternative to this in a moment. Okay, but k equals -1, so in this case now that's going to become minus 2 pi divided by 4, so it's going to be minus pi by 2. So Z3 is going to be equal to cos of minus pi by 2 plus I sine minus pi by 2. And cos of minus pi by 2 is 0, and sine of minus pi by 2 is -1. So this is going to become minus I. Now I'm switching back to the positive, so I can go with 2 now and -2. Okay, so if I do 2, I get that theta is, so 2 times 2 is 4, so it's 4 pi divided by 4, so this is going to be pi. So Z4 is going to be cos of pi plus I sine of pi. And cos of pi is -1, and then sine of pi is 0, so this is going to become 0, and that's going to leave me with -1. Now, these are now my 4 distinct solutions. So 1i, -I, and -1. So now I've done that, let me just show you you know, if I just stuck with doing the positive ones, so I wouldn't have done this -1 here. And, you know, now I'd be looking at k equals 3. So if I'd done that, I would have had 4 theta equals 6 pi. So 6 pi divided by 4 is 3 over 2 pi. So then we would have had z whatever one we're looking at. I'll just call it z at the moment. So that's cos of 3 pi by 2 plus I sine of 3 pi by 2. And cos of 3 pi by 2 is 0, and sine of 3 pi by 2 is -1. So this would have given me minus I. So this would give me the same value as this one. Okay, and it's because of these angles here. So these angles are outside of our range. Okay, 3 over 2 pi. And if I take away 2 pi from it, I get -1/2 pi. Okay, so this is equivalent to this one. And then I can go on, you know, I could do even a k equals 4 and so on. And I'd always find, you know, ones that match up with some of my previous answers here. So, you know, you can just do all positive values of k and then just take away 2 pi or add 2 pi or multiples of it to keep the angle, the argument within the range of -pi to pi. Okay, I prefer to just switch between positive and negative values so that I can keep it in the range just from the beginning without having to manipulate the range. So there we have that z is 1, I minus I and -1. Okay, so it's those 4 are its roots. Now, if we take these 4 solutions and then plot them on an Argand diagram, so the imaginary and the real axes are there, and I'll plot them in red, so, you know, just wherever you want to put 1. So there's 1, I, -1, and minus I. Okay, so these are each of my answers. Okay, and the angle between these is pi by 2. And that's the angle between each of them. And you should recognize pi by 2 from when we were working out those solutions. Okay, so these are, you know, each of my angles. So like Z1, Z2 was I, Z3 was minus I, and Z4 was -1. Now, for this one, you know, this equation equaling 1, in this case, z to the 4 equal 1. Now, that is like a special one. So, z to the power n equals 1 has solutions where z is cos 2 pi k or 2k pi over n plus I sine 2 pi k over n, or e to the 2 pi I k over n for k equals 1, 2, 3, etc. up as far as n. Obviously we use negative ones as well, but it makes no difference. You just want to use consecutive values. Now these are known as the nth roots of unity. Okay. Now what's special about these is that if n is a positive integer, then w equals e to the 2 pi I over n. Okay, and then that gives me my roots. The nth roots are 1 w squared, w cubed, and so on all the way up to w to the power n minus 1. And these roots form the vertices of a regular nonagon. Okay, so they're the vertices of a regular nonagon, n-agon. Okay, also that one, if you add them up all the way up to wn minus 1, they'll always equal 0. Okay, so I'll show you with the solutions that we had. So these were my 4 solutions. Now obviously the 1 is this one here. So let's make w the z2. So let's let w equals to z2, which is equal to I, or which is e to the pi by 2I. Then w squared will be e to the pi by 2I squared. Oh, sorry. The whole thing squared, which will be e to the pi I. Now, e to the pi I was the same as z4, and w cubed, which will then be my 4th root, because when I got 4 roots, it's 1 w squared, w cubed. So w cubed will be e to the pi by 2I cubed, which is e to the 3 pi by 2I, which of course is outside of my range between pi and minus pi. So if I take 2 pi away from it, because it's above pi, so subtracting 2 pi, this will become e to the minus pi by 2I, which of course is the same as my z3. Okay, so each of these now is basically the same as each of these. So if I add them up, so 1 plus w squared plus w cubed, I've got 1 plus I plus z4, which was the minus 1, plus z3, which was the minus I, which of course equals 0. Okay, so that is, just kind of summing up this scenario here, and it just works when you've got z to the power something equals 1. Okay, so really it doesn't really require much calculations, and this of course can be proven. Okay, but we're not doing that. It's not part of our scheme of work. But anyway, that's just looking at z to the power 4 equals 1, and that is of course the most simplest form of question that you will get. Obviously, you're more likely to get something slightly different, so let's look at that. So here I've got z cubed equals 2 plus 2I. So first I want to do a little sketch. So that's my real axis, my imaginary axis, and 2 plus 2I is going to look like this. And it's 2 by 2. So the modulus, first of all, is going to be 2 squared plus 2 squared, and then square rooted. So it's going to be 4 plus 4 is 8. Square root of 8 is 2 root 2. And the argument is going to be arc tan 2 divided by 2, which is going to be pi by 4. So z cubed is 2 root 2 cos pi by 4 plus I sine pi by 4. Now let's write this z in its general form. So that's r cos theta plus I sine theta, and that's raised to the power 3. And then let's write this right hand side and just change it to its general form. So that's going to be pi by 4 plus 2k pi for the angles. So I sine pi by 4 plus 2k pi. Okay, now using de Moivre's theorem on the left, we get r cubed cos 3 theta plus I sine 3 theta equals 2 root 2, and the rest of this stays the same. So now we can compare. So r cubed equals to 2 root 2, and 3 theta equals pi by 4 plus 2k pi. So r equals, now the cube root of 2 root 2 is root 2, although your calculator won't bring that up. So I'll just explain briefly. So we've got this 2 root 2 is root 8, isn't it? And if I take the cube root of that, I've got 8 to the half raised to the power a third. Now, these powers, when you're raising a power to another power, you multiply them. So it's like 8 to the power of 6. But this is also the same as 8 to the third to the power a half, which is 2 to the power a half, or root 2. Okay, so that's just a little kind of manipulation there. It won't show up in your calculator. I think you'll just get the decimal answer. So r is just root 2, and of course 3 theta equals this. We'll obviously divide by 3, but we'll put in our values of k first. So when k equals 0, then we've got 3 theta will equal pi by 4. So theta equals pi by 12. So z1 is root 2 cos pi by 12 plus I sine pi by 12. And for these, you've got to pay attention to what the question asks. It wants the answers in. So if it says it wants it in the form x plus iy, we'd then convert this into that form. Or it might say it wants it in the form r plus cos theta plus I sine theta, which is of course the form that we have here. Or it might say it wants it in the form r e to the I theta, in which case then we would convert this into this form. I've already dealt with this form. We'll do this question in this form, but at the end I'll change into this form just to show you the final of the 3 kind of forms that it could be in. So that's k equals 0. This time I'm just going to do all positive numbers, just to show you can do it with all positives. So k equals 1, then we've got that 3 theta is equal to pi over 4 plus 2 pi. So that means that theta, well, pi by 4 plus 2 pi is 9 pi by 4. Dividing by 3 is 3 pi by 4. So this time then Z2 is root 2 cos 3 pi by 4 plus I sine 3 pi by 4. Now, normally I personally would go to k equals -1 because I know that'll give me a value between minus pi and pi, but we're going to just stick with doing it just the positive ones. And of course, you know, these I keep on going. So if it's 3 cubed, yeah, I'm going to get 3 roots. If it's to the power 4, I'm going to get 4 roots. To the power 5, I'm going to get 5 roots, and so on. So this time we've got 2 for k. So 2k, so 2 times 2 is 4, so this is plus 4 pi. So this is 17 over 4 pi divided by 3. So we got 17 pi by 12. Now this value here is obviously above pi. So if it's above pi, I take away 2 pi. And what I get then is that theta is minus 7 pi by 12. Okay, so now I've got that. That's between minus pi and pi. That'll be my Z3. So it's root 2 cos of minus 7 pi by 12 plus I sine minus 7 pi by 12. And those are my 3 roots. Alternatively, I could write them in terms of E. So I'd have Z1 is root 2e to the pi I by 12. Z2 is root 2e to the 3 pi I by 4, or Z3 is root 2e to the minus 7 pi I by 12. Okay, and there I have my 3 solutions in the form RE to the power I theta. Okay, so in general, 3 different ways in which they might ask for the answer in the form of R cos theta plus I sine theta, in the form R e to the power I theta, or of the form x plus I y, which we did previously. Generally, it might not ask for x plus I y form unless usually when the angles give you nice values that are roots and fractions and things. They don't generally ask for that when it comes up as decimals, but you know, you never know. But usually when it comes up as decimal answers for x plus I y, it will generally be this form or this form. Okay, so that was, you know, a harder set of values, but as you can see, there's nothing too difficult about this. And as you can see here, you don't have to go 0, 1, minus 1, which I normally do is 0, 1, minus 1, 2, minus 2, and so on. You can just do the positive values and then take away the 2 pi to get this angle between minus pi and pi. Okay. After this, then any other values, subsequent values of k, will just create duplicate answers. So answers that when you add or subtract 2 pi to, you'll get one of these 3 angles. Okay, so there's that example done. Now I'm going to do another example, but just showing a different way of getting to the answers. So instead of writing it in this form, cos theta plus I sine theta, or r cos theta plus I sine theta, if we start off and we write it in this form, re to the I theta, like how do we solve it that way? Because what I want to do is I don't want to give you just one way of solving a problem. If there's more than one way that is within the spec, I want to make sure I show you all ways so you can pick whichever way you feel more comfortable with. So here we've got a question, z to the power 4 minus 3 equals 4i. So change that into z to the power 4 first on its own, and that's 3 plus 4i. So first things first, we need to find the modulus and we need to find the magnitude, so the argument. So 3 across, 4 up, and we have this. So the modulus is going to be 3 squared plus 4 squared, and then square rooted. And that's going to give me 5. And the argument is going to be arc tan 4 over 3. Now, this isn't going to be a nice fractional angle, so we're going to do it in radians. Obviously, it's all in radians, and we're going to do it to 3 significant figures, or 3 decimal places. Okay, so that's what it is. I've stored the full answer in my calculator, and I stored it as A in my calculator. Not that that helps you, it's just to help me. Okay, so our answer in this case is going to be basically in decimals. So this time I said we'll do it in a different form. So we've got our z4, z to the power 4 I should say. So that z is r e to the I theta, then to the power 4. And that's going to be equals to 5e to the 0.927 plus 2k pi I. Now this is going to be r to the power 4 ei to the 4 theta, but obviously it'd be better if I just write the 4 theta first, I think. So 4 theta I equals 5e to the 0.927 plus 2k pi I. So r to the 4 equals 5. So r is 5 to the quarter. So I'll put that as 5 to the power 0.25. Then I've got 4 theta is equal to 0.927 plus 2k pi. So this is what I'm dealing with. So k equals 0. So straight away 4 theta equals 0.927. Therefore theta will be that divided by 4, which is 0.232 to 3 significant figures there. Okay, so that means that it is 5 to the 0.25 e to the 0.232 I. Now let's do k equals 1. So that is 0.927, which I've stored as A, plus 2 pi. So that is 7 point something, divide by 4, and that is 1.803, We'll do this to 3 decimal places, I think, rather than 3 significant figures, just because I feel this will be a little bit better. So that will be 5 to the 0. So I forgot to put Z1 equals Z2 equals e to the 1.803i. Let's put k equals 2n. So now we've got 0.927 plus 4 pi. So that's 13 point something. Divide by 4 and we get, this is 3.373. Now this is bigger than pi, isn't it? Because pi is 3.141 and so on. So for this one now, I need to take away 2 pi. So this is therefore minus 2.910. Okay, again to 3 decimal places. So Z3 is 5 to the 0.25 e to the minus 2.910i. So I've done 3 solutions, or 3 roots. So next to do k equals 3. So that is 0.927 plus 2 times 3 is 6, so plus 6 pi. So that's 19 point something. Divide by 4, and that is 4.944, which of course is bigger than pi. So take away 2 pi, and we get, it's the same as minus 1.339 to 3 decimal places. So Z4 is 5 to the 0.25 e to the minus 1.339i. And these are my 4 solutions, which I've done now using RE to the I theta for the working out and getting them through to the answers. So decide which way you want to do it, whether you want to keep it in terms of cos theta I sine theta, or whether you want to do it in terms of RE to the I theta. Or if you're comfortable in both ways, you know, you could do it this way if you needed the answer in this form, and you could do it in the cos theta plus I sine theta if you needed the answer in that form, and do it that way. It's totally up to you how you go about doing this. Just make sure you practice, and like I said, you know, in the first one where I use negative values, you can use negative values. I personally generally use the negative values so that I don't have to take away the 2 pi's, but like you can see, it's just as easy to do all positives and then the minus the 2 pi's if you're over, or in some cases you take away 2 pi. So that's kind of all it is to it in terms of the examples. Hopefully you found this video useful so far. If you have, please hit the like button, subscribe if you're yet to subscribe, and if you're willing and able to help me out financially, then hit that join button. Otherwise, let's look at a couple of questions. So I've got 4 questions for you. First is a nice straightforward one, given in the form x plus iy. Second one, just like the last 2 examples, given the form r equals cos theta plus I sine theta. And then these are 2 past paper questions. So this one is given it in the form r equals I theta. So then the 3 questions here, you've covered all 3 forms. And this one again is also in the exponential form there. So there's a 4th question there. But all 4 forms, now these are worth, I think this one was worth 6 marks and this one was worth 7 marks in the actual exam, the work was very similar with 4 roots and a diagram. Okay, so you know, you can see that it's going to be 6 or 7 marks for these types of questions depending on the exam. They might, you know, modify the marks because they want to get the same total every time. Anyway, I'm rabbiting on. Pause the video now to have a go at these questions. Welcome back. Now let's have a look at the solutions. So first let's write this as z cubed equals 27, and then that is z cubed equals 27. Now I'm going to put it in the form of cos theta plus I sine theta, so that's cos 0 plus I sine 0. Okay, because we want the real part and we don't want the imaginary part. Now let's write z as r cos theta plus I sine theta, and then put that to the power 3, and 27 cos. Now we want 0 plus 2k pi plus I sine 0 plus 2k pi. And that is r cubed cos 3 theta plus I sine 3 theta, with the right hand side staying the same. So r cubed equals 27, so r is 3, and then we've got 3 theta equals 0 plus 2k pi. Okay, or I can get rid of that 0 and just call it 2k pi. So now when k equals 0, theta also equals 0. So this one is going to be z1 equals 3 cos 0 plus I sine 0, which is just going to be 3. Now k equals 1 is going to be, theta is, so 2 pi divided by 3, so 2 pi by 3. So therefore z2 is going to be 3 cos 2 pi by 3 plus I sine 2 pi by 3, which is going to be 3 times minus a half plus root 3 over 2i. So that's going to be minus 3 over 2 plus 3 root 3 over 2i. And then k equals 2. We've got, so that's going to be 4 pi by 3. Now 4 pi by 3 is obviously bigger than pi, isn't it? So I'm going to take away 2 pi from that, and I get that this is the same as minus 2/3 pi. So z3 is going to be 3 cos minus 2/3 pi plus I sine minus 2/3 pi. And that's going to be 3. And it's going to be minus a half minus root 3 over 2i. So that's going to be minus 3 over 2 plus, minus 3 root 3 over 2i. So those are my 3 solutions to this one. Okay, so that's question 1 done. So this one's in the form of r cos theta plus I sine theta. So z to the 4 equals minus root 7 plus 3i. Now this one, I need to work out what the angle is. So minus root 7 is to the left, 3i is up. So we've got 3 there and root 7 there. Now this is going to be my theta. So the modulus is going to be 3 squared plus 7 and then square rooted, which is 4. Now working out alpha first. So alpha is arc tan 3 over root 7, which is 0.848. Now we actually want theta, and theta is going to be pi minus that alpha. So that'll be pi minus alpha. So theta is going to be 2.29. We'll do it to 2 decimal places in this case. Okay, so but I will store the full answer in my calculator for all of the working outs. Right, now let's look at what we've got for our Z4. So Z4 can be written as R cos theta plus I sine theta, and that is raised to the power 4. And then we've got 4 cos, now this is 2.29 plus 2k pi plus I sine 2.29 plus 2k pi. Okay, which is r to the power 4 cos 4 theta plus I sine 4 theta, and the right stays the same. So we get r to the power 4 equals 4. Therefore, r is going to be equals to root 2. And then we've got 4 theta equals 0.2, sorry, not 0.29, 2.29 plus 2k pi. So when k equals 0, 4 theta equals 2.29 divided by 4, so theta is 0.573, but again we'll just do it to 2 decimal places. So Z1 equals root 2 cos 0.57 plus I sine 0.57. Now let's put k equals 1 in. So that now is our 2.29 plus 2 pi, which gives us 8 point something. Divided by 4 is 2.14. So still within the range. So 2.14, of course the 2 decimal places. So Z2 is root 2 cos 2.14 plus I sine 2.14. And that is our second solution. Remember, there's going to be 4 solutions in this case. Now we've got k equals 2. So that's 2.29 plus 4 pi this time. So that gives me 14 point something. Divide by 4. This now gives me 3.71, which is greater than pi. So I'm going to minus 2 pi from that, and I get minus 2.57 to 2 decimal places. So that is my Z3. It's root 2 cos minus 2.57 plus I sine minus 2.57, and there we have it. And then finally k equals 3. So we got our 2.29 now times by 3, so it's going to be 6 pi. So plus 6 pi gives me 21 point something divided by 4, and that's 5.29, which is greater than pi. So minus 2 pi, and we get that this is minus 0.997. Oh, so it's going to be actually minus 1.00 when I round to 2 decimal places there. So Z4 is root 2 cos minus 1.00 plus I sine minus 1.00, and that is my 4 solutions complete. Now the first of the exam questions. So first the modulus and argument of minus 2 minus, so it's down here, and it's going to be 2 in this direction and 2 root 3 in this direction. So I call this alpha and this will be theta. Remember that the modulus is from 0 to pi and 0 to minus pi, because it's between minus pi and pi. Okay, that's the argument. So modulus is going to be that minus 2 squared plus minus 2 root 3 squared, and then square rooted. And that's going to be 4. Now, alpha is arc tan 2 root 3 over 2, which is going to be pi by 3. So that means that theta is going to be 2 pi by 3, and it's going to be negative. Okay, so I've got my modulus and I've got my theta. Okay, oh, I only needed the modulus for the first part. Oh no, I did modulus and argument, that was the first part. Right, part B, find the solutions, hence find the solutions to this. So if I rearrange it, I get minus 2i root 3. So that now, is the same as that. And we need to give it in the form re to the I theta. So let's, for a change in this case, do it all in exponential. So I'm going to do re to the I theta to the power 4 equals 4e to the minus 2 pi by 3 plus 2k pi I. Okay, so r to the 4 e to the 4 theta I equals 4e to the minus 2/3 pi plus 2k pi I. So r to the 4 equals 4. So this means that r is going to be root 2. 4 theta is equal to minus 2/3 pi plus 2k pi. So there's my nice setup. Now let's go with k equals 0. So when k equals 0, I've got minus 2/3 pi and then divide by 4. So theta is minus pi by 6. So I'm going to do this one underneath. So z, oh, I could do it alongside. It doesn't matter now, I've started. So z1 equals root 2 e to the minus pi by 6 I. Now k equals 1. So when I add 2 pi to the minus 2/3 pi, I get 4/3 pi. Divide by 4, isn't it? We get pi by 3. So z2, oh, I've written this alongside now, is root 2 e to the pi by 3I. K equals 2. So when k equals 2, that means I'm doing minus 2/3 pi plus 4 pi, which is 10/3 pi, which is too big, isn't it? So let me just change that into a 3, which is, more than, oh, I haven't divided by 4. Divide by 4. Which is 5/6 pi. There we are, it's not too big. So this is root 2e to the 5 pi by 6I. And then k equals 3, we get, so minus 2/3 pi plus 6 pi this time. Divide by 4 gives me 4 pi by 3, which is too big, so minus 2 pi, and we get minus 2 pi by 3. So z4 is equal to root 2e to the minus 2 pi by 3I. And there we have our 4 solutions. Now all that's left is to draw this on an R-Gann diagram. I'll just make some room on the right. And these will basically have because there's 4 of them, they can have a 90-degree angle between them. Okay, so it's going to be like 1 here and 1 here. And 1 here and 1 here. So this one is my root 2e to the pi by 3I, and opposite it was root 2e to the minus 2/3 pi I, and then in my top left was root 2e to the 5 pi by 6I, and then the bottom right is root 2e to the minus pi by 3I. Okay, just in terms of angle size, so 1/3, 2/3, 1/3, 5/6 there. Now these will also, because they're all the same length, they'll also be kind of the points on a circle. So if I had a circle with this is the radius, the magnitude here, then that would be my circle. Okay, so just for you to be aware, these will all finish on the circumference of a circle with this radius. So there's that done and part B complete. Now let's look at the final question. So again, past the exam question. So let's multiply by 2 first to get rid of the brackets. So 2 minus 2i root 3. Now we've got to get this in exponential form and show it on an R-Gann diagram. So let's go ahead and work out the modulus and the argument. So it's 2 across minus 2 root 3 down. So it's like down here, 2, and this is 2 root 3. I can call this alpha, and then it's actually the theta, isn't it? There. But anyway, right, modulus is going to be 2 squared plus 2 root 3 squared. I feel like we've already had this one. And then the argument is going to be 2 root 3 over 2 and shift tan there. So the argument is going to be minus pi by 3 because it's below the 0 line there. Okay, so I've got my modulus and my argument. Now, let's rewrite Z4 as r e to the I theta to the power of 4. And this is going to be 4e to the minus pi by 3 plus 2k pi I. This is r to the 4 e to the 4 theta I equals, and the right hand side stays the same. Oh, this one's quite straightforward. It's again very much like the previous one where r is the same there. And then we've got 4 theta equals minus pi by 3 plus 2k pi. Yeah, it's very much like the last one. They weren't very creative in these two exam questions. Right, so when k equals 0, so we've got minus a third pi, obviously plus 0 stays as minus third pi, divide by 4, so we've got then that theta is minus pi by 12. So Z1 is going to be root 2e to the minus pi by 12i. Now when k equals 1, we have, so we've got our minus a third pi plus 2 pi, gives me 5/3 pi, divide by 4, and that gives me 5 pi by 12. So Z2 is root 2e to the 5 pi by 12i. K equals 2. So again, starting off with my minus a third pi, this time plus 4 pi, we get 11 over 3 pi, divide by 4, get 11 pi by 12, which is again within my range. So root 2e to the not the minus, to the 11 pi by 12i. Now k equals 3. So again, starting off with my minus third pi plus 6 pi this time. Divide by 4, we get 17 pi by 12, which is obviously outside of our range. So minus 2 pi from that, and we get minus 7 pi by 12. So Z4 is root 2e to the minus 7 pi by 12i. So those are my 4 solutions. And then drawing these on an argon diagram, it's going to look basically like the last one. So we've got our 5 pi by 12i here, 11 pi by 12i here. Then this is minus 7 pi by 12i, and then minus pi by 12i here. So pretty much the same, the angles between them all are pi by 2 between each of these, just like the last one. And again, they would form the points on a circle. Okay, so, well, the same circle as the last one, basically. But there you have it. So those are the 4 questions, and that's the finding the nth roots of a complex number. Okay, hopefully if you didn't understand this before, you do get it now. It is quite straightforward, and I do advise you to perhaps maybe stick with one method if you're a little bit unsure of this. But if you are, a bit more confident, understand it a bit more, then switch between the, whether you do it as exponential or whether you do it in terms of cos theta and I sine theta. Okay, so that is that, and that is the third chapter complete. Okay, but we're sticking with Argand diagrams and complex numbers as we move on to now further Argand diagrams.